Hello. In this chapter, we will be going over aldehydes and ketones. Although we have seen them throughout Organic 1 and 2, in this chapter we will be talking exclusively about them and some of the reactions that they undergo. By the end of the chapter, we'll be able to compare the structures of an aldehyde and a ketone, assign IUPAC name for aldehydes and ketones, describe 3 methods for synthesizing aldehydes and 4 methods for synthesizing ketones, explain why the carbon of a carbonyl group is susceptible to nucleophilic attack, and why aldehydes are more reactive than ketones, as well as describe mechanisms for nucleophilic addition under basic and acidic conditions. Explain the process of reduction of ketones or aldehydes with hydride-reducing agents. Describe the reactions of aldehydes and ketones with a Grignard reagent, with hydrogen cyanide, and a Wittig reagent. Describe how a ketone or aldehyde can be converted into a hydrate, acetal, heme acetal, or a cyclic acetal, and explain why acetals can function as protecting groups. Explain the process of imine formation, including formation of carbinolamine, hydrazone, and oxide, and an enenamine. Describe the conditions for and mechanisms of acetal, imine, and enamine hydrolysis. Describe how the Wolff-Kishner reduction transforms ketones to alkanes. Describe the reaction of ketones with peroxyacids and the mechanism of the Baeyer-Villiger oxidation. Identify the products that can be made from aldehydes and ketones and the reagents required for the reactions. And lastly, describe the characteristic signals of the IR and NMR spectra for aldehydes and ketones. Aldehydes and ketones have a few things in common, including the presence of a carbonyl group. So you can see here, both in the carbon, aldehyde, and the ketone. They are important in both biology and in industry. We have a few examples. We have formaldehyde, for instance, very common in nature, as well as acetone. We have a few that you may be familiar with. We have vanillin, cinnamaldehyde, carbone, benzaldehyde, and progesterone and testosterone. So you can see they have aldehydes, ketones, aldehyde, and so on. Now, when we're naming aldehydes and ketones, the process is one that you're already familiar with. We're just going to apply it to this new set of functional groups. There are 4 steps in naming aldehydes or ketones, same procedure as with everything else we've discussed. First, we identify and name the parent chain. Then, we identify the name of the substituents, assign the number to each substituent, and assemble the substituents alphabetically. So, let's start with the first step, identify and name the parent chain. For aldehydes, once we identify the parent chain, we substitute the E that you see at the end of an alkane with Al. So butane becomes butanol, for example. The parent chain must include the carbonyl carbon. Super important. For example, here we have an octane as a parent chain, and you will be tempted to pick out the longest chain, which makes a lot of sense, except that in this case, the longest chain must also include that carbonyl. So for instance here, it will be hexane, right? Hexane 6 and Al because it's an aldehyde of hexanol. The aldehyde, the carbon that contains that aldehyde is usually assigned the number 1 when possible. So for example, here you have 2 options, left to right, right to left. You pick the order in which that aldehyde will be your first carbon atom. For ketones, instead of using Al, we're going to use ONE. So that same butane that we use as an example becomes butanone, right? ONE. Parent chain must include the carbonyl group, just like with aldehydes. The carbonyl carbon is given the lowest number possible and can be expressed before the parent name or before the suffix. So we have 2 ways of naming this. For example, here, 7 carbon atoms. Our carbonyl is in carbon number 3. So this can be either 3-heptanone or heptan 3-ONE. Either is accepted. IUPAC also recognizes the following common names as parent names. This more because of the historical perspective than anything else. So formaldehyde, acetaldehyde, benzaldehyde. These are names that you will see in industry, you will see in the labs very commonly. They're not necessarily IUPAC names, but they're IUPAC approved common names. The Let's go over a few methods that we already know for preparing aldehydes and ketones. First, oxidation of primary alcohols. When treated with a strong oxidizing agent, primary alcohols are oxidized to carboxylic acids. Formation of an aldehyde requires a mild oxidizing agent that will not further oxidize the reducing aldehyde. We learn about this in our CHEM 1, just as we learn most of the ones that we'll be seeing in this section. Ozonolysis of alkenes. Ozonolysis will actually cleave or break this double bond. If either carbon atom bears a hydrogen, then you get an aldehyde. Hydroboration followed by an oxidation of terminal alkynes. This results in an anti-Markovnikov addition of water across the pi bond, followed by tautomerization of the resulting enol to form an aldehyde. Oxidation of secondary alcohols. This can happen via a strong oxidizing agent or a more mild one, like the PCC you see here. The resulting ketone does not undergo further oxidation. Ozonolysis of alkenes. Tetrasubstituted alkenes are cleaved to form ketones, so this breaks. You get oxygen atom on one side, oxygen atom on the other. You get two ketones. Acid catalyzed hydration of terminal alkynes. This procedure results in a Markovnikov addition of water across the pi bond, followed by a tautomerization to form a methyl ketone. Lastly, a Friedel-Crafts acylation. Aromatic rings that are not too strongly deactivated will react with an acyl halide in the presence of a Lewis acid to produce an aryl ketone. Now let's talk a little bit about the reactivity of that carbonyl bond. The carbonyl bond is electrophilic. This is derived from two effects: resonance, as you can see here, and induction. The carbonyl carbon is attacked by nucleophiles, forming new sigma bond in exchange for the carbonyl pi bond, and becoming a tetrahedral center. As you can see, you get the attack here, lone pair of electrons moves, and the resulting would be from going from a trigonal structure to a tetrahedral structure. Aldehydes are generally more reactive towards nucleophiles than ketones. There's two reasons for that. First one has to do with steric effects. Aldehydes are less sterically hindered. Remember, that's just a hydrogen atom versus an R group that ketones have. The second effect has to do with electronic effects. Aldehydes have a larger dipole distribution on the carbonyl carbon. So what that means is that this is going to be slightly more electronegative and this is going to be slightly more electropositive. That actually weakens this area, making it so that the reactivity increases. Aldehydes and ketones react with a variety of weaker nucleophiles under acidic conditions. The main or generic mechanism is illustrated here. We see first a nucleophilic attack. We have a reducing agent such as lithium aluminum hydrate that will donate or deliver the hydride ion that you see here, and then the pair of electrons moves towards the oxygen. That's why you get this right here, that oxide, and then you get a protonation via a hydronium. Now for this to happen, you need that hydronium, so you need to have acidic conditions. Does it have to be very acidic? Not at all. Slightly acidic conditions are just enough. So anything shy of that pH 7 will be enough for this reaction to proceed. Looking back, recall that Grignard reagents attack ketones and aldehydes, and they make an alcohol with a new carbon-carbon bond, just like we've discussed in the past. Either face of the carbon is attacked by the nucleophile. Now this is very important because if you have, as a result, a carbon that has 4 different groups, right? You have that chiral carbon. Statistically, the attack can come from either side, and if it can come from either side, that means that it will. So you get a racemic mixture. The Grignard reaction is consistent with basic conditions, so for that you actually need a higher pH. As you can see, the mechanism similar to what we just saw. You get the attack here on the carbonyl, the electrons on that pi bond move to the oxygen, you get the alkoxide, you get the attack, you get the protonation. Looking at the cyanide ion, cyanide from the hydrogen cyanide is also a carbon-based nucleophile and reversibly adds ketones and aldehydes to form cyanohydrin. The cyanohydrin has the cyanide and then an OH attached to the same carbon. This reaction will work a lot better under basic conditions, so we usually add just enough base to drive that pH higher than 7, and that's it, not more than that. Under basic conditions, as you can see, the attack is very similar to what we've seen so far. You have the attack here on the carbon, pair of electrons move, and then you get that protonation. The addition of acid in this step is really not necessary for the cyanide, let's say, route, because hydrogen cyanide serves as its own source of protons. Looking at the Wittig reaction, this one is extremely important in organic chemistry because just like with Grignard reagents, this carbon skeleton is modified. So it's not just a change in functionalization, you're essentially changing the number of carbon atoms in that molecule, and that's actually kind of a big deal in many cases. Ketones or aldehydes can be converted to an alkene with the formation of a new carbon-carbon double bond, as you can see here from the Wittig reaction. The Wittig reagent, which is what we need for this reaction to happen, is a phosphorus halide in which a carbon atom acts as the nucleophile. So you can see here, this is actually fairly unique, similar to what we saw with the cyanide. So it's not really unique, it's more like uncommon. The carbon possesses the negative charge, and then the resonance is sort of stabilizes. Halide, as a definition, is a neutral compound that contains a negatively charged atom adjacent to a positively charged heteroatom, so something different than carbon. The mechanism is likely a 2+2 cycloaddition between the Wittig reagent and the carbonyl group. We see the proposed mechanism. It's the most likely path that we know of. You see the attack here, and then the electrons on the pi bond, instead of going to the oxygen, they go to the phosphorus in this case. So that will be the 2+2 cycloaddition. You get a cyclic compound, migration here and here, so they break, and you get two different molecules as a fragmentation as a product. The formation of the specially stable triphenylphosphine oxide, this one right here, byproduct drives the equilibrium to favor the formation of the desired alkene. So this is actually favored because this is very stable. A given Wittig reagent is synthesized in 2 steps from the corresponding alkyl halide. It's actually very straightforward to get this reaction. You get the phosphine, it attacks the carbon, the halogen leaves, you get the carbocation, which can then become functionalized by adding this pair of electrons here. This hydrogen migrates, and you get your Wittig reagent. In the presence of water, a ketone or aldehyde will be in equilibrium with this hydrate. Now, this equilibrium doesn't really favor the hydrate, so you'll get this in trace amounts, except when you have very simple, very small aldehydes. The reaction is slow unless you force it via acidic or basic conditions. Under acidic conditions, the carbonyl is protonated and water will be acting as the nucleophile. So you can see this mechanism. You get a pair of electrons from oxygen will be attacking that hydronium, getting protonated. From there, you have the positive charge on your oxygen. You get the attack on the carbon of that carbonyl, eventually leading to that doubly protonated species. Now, when we're going over the mechanisms, keep the following in mind. It sounds like very obvious until it's not, right? So under acidic conditions, any mechanism that you propose must be reasonable, and therefore, if it's acidic, then it must avoid the use of strong bases. The opposite is also true. If it's something that should happen in a basic media, then you shouldn't be counting on that hydronium. For a number of reasons, right? There's one listed here. A strong base cannot exist in an acidic environment. Now, alcohols can attack ketones or aldehydes and they form what we call an acetal. This is actually in an acidic media. That's why you get that H plus here. Under acidic conditions, one ketone or aldehyde will react with two equivalents of alcohols to form an acetone. For that, we usually use acidic catalysts such as sulfuric acid or para-toluene sulfonic acid. So this will be para position. This part right here is for the toluene, and then the sulfonic, so para-toluene sulfonic acid. Mechanism for that reaction: you start off with a protonation, followed by a nucleophilic attack. Then you get a subsequent deprotonation, right, of that and that group that got added in the nucleophilic attack. In this case, you already have the hemiacetone, so just one group is formed. Now you get another protonation, and protonation happens because this right here is not really a good leaving group, but this right here definitely is. Now, once that happens, then you get another nucleophilic attack followed by a subsequent deprotonation, and you get your acetone. So if you break this, this is your first half, this is the second half, so it's basically just same cycle over and over until you get the entire acetal molecule. Acetal formation is an equilibrating process. For most simple aldehydes, the acetal is favored at equilibrium. So that's likely what you'll get if you buy a bottle of a liquid ketone or aldehyde and you leave it there for a long enough time. So in this case, we have ethanol and we have formaldehyde. You get the two equivalents here, so the acetal formation with those ethyl groups or those ethoxide groups added there. For most ketones, the acetal is not favored at equilibrium. In other words, if the aldehydes are small and you leave them there for a while, chances are that you're going to end up with this. But in the case of a ketone, that is actually much less likely to happen. Now, if we talk about a diol, those two OH in a molecule, then both equivalents of the alcohol can come in from the same compound, and you get something a little bit different. You get a cyclic acetone, simply because you're getting attached here, you're getting attached here, and it sort of closes the molecule into what we call a cyclic acetone. Acetal formation is reversible, so it's a good thing, and can be controlled by adding or removing water. To favor the acetal formation, we remove water from the reaction, and to convert the acetone back into the ketone or aldehyde, then we add water with a acid catalyst. So just a few drops of a strong acid is enough. In this way, acetones can be used as protecting groups for ketones or aldehydes. So how does that work? First, we protect the ketone, basically turn it into a cyclic acetone. When this happens, then this isn't going to be changing anytime soon. And then you can take the rest of the molecule, transform it into whatever you need. In this case, we can reduce the ester and deprotect the ketone. So overall, you get this. You're protecting, you're reacting, you have a reduction, you have an addition of an acid. And as you can see, we took that carbonyl and we protected it. We took the ester and we turned it into an alcohol without actually affecting this carbonyl. So that's the whole point of having that extra step of the cyclic acetal formation. Hemiacetal is the intermediate formed in the conversion of a ketone or aldehyde to an acetal. We actually saw that in the mechanism just a few slides back. They are generally difficult to isolate, as equilibrium either favors one side or the other. Rarely does it favor something in the middle. However, cyclic hemiacetals can usually be isolated. Again, that cyclic nature serves a very convenient purpose. A cyclic hemiacetal is possible when a compound contains both the carbonyl group and the hydroxyl, just like the one we see here. We turn this into, so basically we close it off, we form a ring, then this is actually favored equilibrium, and then we can actually either protect it or whatever it is that we need to do with this structure. Cyclic hemiacetals are important in carbohydrate chemistry. So here, when you have the open chain versus the cyclic or the closed chain, the reactivity changes dramatically, right? So you go from very reactive to relatively unreactive. This is an example. Now let's talk about what happens when we want to add nitrogen to the mix. Under acidic conditions, aldehydes and ketones react with primary amines to form an imine. amine, you have the nitrogen, you have the R group, right, associated with the nitrogen, and then you get the functional group imine. The reaction requires acidic conditions to work. This is the post mechanism. We start off with a nucleophilic attack, just like we've been doing throughout the chapter. Right? You attack the carbon, pair of electrons move to oxygen, followed by a protonation, and then a deprotonation, not of this OH, but rather of the newly added group. Once that happens, you have a carbonyl amine, so carbonyl, and then amine. We protonate, and why do we protonate? Because this is a bad leaving group, but this is a really good leaving group. We want it removed, and then we deprotonate the nitrogen containing, we form the imine. So these are several steps, but as you can see throughout this chapter, we've basically gone over one mechanism and we've applied it in a bunch of different contexts. So once you know that mechanism, you know how to apply it, you should be okay with changing context a little bit between one section and the other. But even though it is under acidic conditions, protonation of the carbonyl is not the first step of imine formation mechanism. So basically what happens, you have the amine, you form the ammonium ion under acidic conditions. This is actually very common, we know this from general chemistry. The ammonium ion is not acidic enough to protonate an aldehyde or a ketone, but it is acidic enough to transfer a proton to a negatively charged oxygen in a subsequent step. So this isn't going to be the initiator, but it will participate eventually in the process. We actually saw that in the mechanism one slide back. Under acidic conditions, aldehydes and ketones react with secondary amines to form an amine. So kind of what we see here. The reaction requires acidic conditions to work. The mechanism is identical to amine formation except for the last step. Let me show you. So nucleophilic attack, followed by a protonation, deprotonation, and then subsequent protonation, loss of the leaving group. So all of this we've seen before. Now this deprotonation actually changes this last part right here. You get a deprotonation step here, pair of electrons migrate, and you get the N-amine. That's how you get that double bond right here. The reaction requires acidic conditions to work. The mechanism is identical to imine formation, except for the last step, just like we saw. And then basically this is sort of the pathway between the N-amine and the imine, just for comparison. Acetals are hydrolyzed with aqueous acid to yield a ketone or an aldehyde and two equivalents of alcohol. So basically you're going in the other direction now. Acetals will only react with water under acidic conditions. So if you don't want to have that acetal react, what do? You increase that pH, right? Over above 7, it should be okay. Here is the mechanism of reaction. As you can see, it's exactly the same as we've seen so far. Except that now we're moving sort of in the opposite direction. Instead of going from the ketone to the acetal, we're going from acetal to ketone. Everything else is basically the same. Hydrolysis of imines and enamines undergoes a very similar mechanism under acidic conditions. The mechanism of hydrolysis for imines and enamines is simply the reverse of their mechanisms of formation. Those mechanisms we saw a few slides back, just flip the arrows and you end up here. Now let's talk a little bit about the Wolff-Kishner reduction, which is a two-step synthesis converting a ketone to an alkane. First step is imine formation between ketone and hydrazine, which is like a primary amine. After that, we undergo an elimination. So let's look at that mechanism. It's a little bit different now. So we're going to start first with a deprotonation. You can see here, we have an OH, so this is going to be in basic conditions. We have that attacking that proton. The pair of electrons move to nitrogen. You get a negatively charged nitrogen as a result, which is stabilized via resonance. After that, you get a protonation of that carbon. You can see here. Followed by a deprotonation of the nitrogen. After that, you get the loss of a leaving group, followed by a protonation step. And that's it. The Baeyer-Villiger oxidation, in this case, an oxygen is inserted into an aldehyde or ketone between a carbonyl carbon and a neighboring alkyl group. So this one is very interesting because you're adding an oxygen either here or here, and then the oxygen sort of gets in there. An aldehyde or ketone is converted to a carboxylic acid or an ester. So this is one of the ways in which we are able to sort of manipulate or form that ester or that carboxylic acid outside of your Fischer esterifications, for example. Cyclic ketones produce lactone, in other words, a cyclic ester. For an aldehyde or unsymmetrical ketone, the rate of migration is as follows. Tertiary is going to have a higher rate than secondary, followed by phenol, which are about the same as a secondary, which is larger than primary, which is larger than methyl. Now, what should we expect in terms of spectroscopic analysis? Well, you already know a little bit of this. We'll talk a little bit more about those carbonyl peaks. They're going to be a little bit different between a ketone and an aldehyde. Conjugated carbonyls stretch at a lower wave number. So the higher that conjugation, the lower the wave number should be. You can see a relatively large actually stretch between 1715 and 1680. Increasing the ring strain increases the wave number. So as the number of carbons in that ring goes down, then the wave number goes up. Aldehydes also give weak peaks around 27-2800 for that carbon-hydrogen stretch. But we really focus more on that carbonyl, more so than anything else. Here, for example, we have an aldehyde. They give you absorbances between 27 and 28. And then, of course, the carbonyl stretch, which is what usually we see a little bit faster, a little bit more obvious. Protons neighboring a carbonyl are weakly de-shielded by the carbonyl and appear +1 ppm downfield. Aldehyde protons are strongly de-shielded around 9 to 10 ppm. So for example, here we have an aldehyde. You can see that first proton right here. Then you see the ones for your aromatic, and then the ones from here. Carbonyl carbon produces a weak signal near 200. This is carbon anymore. And then the rest of the signals 1, 2, 3, 1, 2, 3. And here this is a summary of the various reactions that we've seen so far involving ketones and aldehydes. Try to treat them as one group, right? The main difference is that aldehyde have a proton where ketone will have an extra R group. Outside of that, most of these reactions will apply. All of these reactions actually will apply. So this is just a summary. Make sure that you go over this whenever you're studying for your test.